I bet you didn't know how crucial building automation control valves are to the comfort and efficiency of every modern building. Welcome, future engineer. Whether you're just starting your journey in the world of building systems, or you're looking to sharpen your skills, you're in the right place. Today, we're about to embark on an exploration of a topic that's absolutely essential for anyone working with heating, cooling, or water systems in buildings: valve sizing, especially when it comes to building automation control valves. Valve sizing might sound technical, but it's the foundation of comfort, efficiency, and reliability in any building. Imagine walking into a perfectly climate-controlled room where the temperature is just right and the system runs quietly in the background. That's the magic of proper valve sizing at work, especially for control valves in automated systems. Think of a building's heating and cooling system like your body's circulatory system. Pipes are veins, water is blood, and valves are the muscles controlling flow. Just as your heart and muscles work together to keep you healthy, valves and pipes must be perfectly matched to keep a building running smoothly. Get the valve size wrong, and you risk blasting a tiny plant with a fire hose or trying to fill a pool with a squirt gun. Either way, it's a disaster. Too much or too little flow can cause all sorts of problems, from noisy pipes to uncomfortable rooms and even system failures. Oversized valves cause jerky temperature changes and waste energy. Undersized ones choke the system and overwork pumps. The result? Higher energy bills, more maintenance, and unhappy building occupants. Valve sizing is about matching the valve to the job, ensuring comfort, efficiency, and quiet operation. It's a blend of science, engineering, and a bit of art, balancing flow, pressure, and system needs. When you size a valve correctly, you save energy, money, and help the planet. Efficient systems mean less waste, lower carbon footprints, and a more sustainable future for everyone. In this guide, you'll learn about ball, globe, butterfly, and pressure-independent valves. Each type has its own strengths, weaknesses, and ideal applications, especially when used as control valves in building automation. We'll show you what makes each one unique and how to pick the right size. You'll discover how to read system requirements, interpret technical data, and make smart choices for any project. There's even a bit of simple math to make you a sizing pro. Don't worry, it's easier than you think, and we'll walk you through every step with clear examples and practical tips. By the end, you'll be ready to tackle your first valve sizing project with confidence. So grab your notepad, get comfortable, and let's dive in together. The world of building automation control valves awaits, and your journey to becoming a building systems expert starts right now. First up, let's talk about the ball valve, one of the most common and recognizable types of valves you'll encounter in industrial settings, commercial buildings, and even in your home plumbing. Ball valves are everywhere, and for good reason. They're simple, effective, and incredibly reliable. Inside the valve body, there's a spherical ball with a hole drilled through its center. This ball acts as a straightforward on-off switch. When you turn the handle, you rotate the ball, aligning the hole with the flow path to open the valve, or turning it perpendicular to block the flow and close the valve. It's a simple mechanism, but it works beautifully. Think of ball valves like the light switches of the piping world, perfect for situations where you want the flow to be either fully on or fully off. They're not designed for fine-tuning or throttling the flow, so if you need precise control, you'll want a different type of valve. One of the biggest advantages of ball valves is their straight-through flow path. This design means there's very little resistance to the fluid moving through the valve, which helps maintain system efficiency and reduces pressure drop. Ball valves are also known for their ability to provide a tight leak-proof seal. When closed, the ball presses firmly against the valve seats, making them ideal for shut-off applications where you can't afford any leaks. However, if you try to use a ball valve to control flow precisely by leaving it partially open, you'll run into problems. The partially open ball creates turbulence, which can lead to noise, vibration, and even premature wear on the valve components. Sizing a ball valve is refreshingly straightforward. All you need to do is match the valve size to the pipe size. This ensures you get the best performance and avoid unnecessary restrictions or complications. For example, if your system uses a 2-inch pipe, you'll want to install a 2-inch ball valve. This keeps everything flowing smoothly and makes installation a breeze. By keeping the valve and pipe sizes consistent, You maintain an efficient, simple, and easy-to-maintain piping system. It's one less thing to worry about during design and maintenance. Ball valves are your go-to choice when you need to shut off flow quickly and reliably, whether it's for routine maintenance or in an emergency situation. But if your application calls for fine adjustments or precise flow control, you'll want to look at other valve types, like globe or needle valves, which are designed for that purpose. So, that's the ball valve. Simple, robust, and perfect for on-off control. Easy, right? Let's move on to the next type of valve and see how it compares. Meet the globe valve, the artist of precision control. Unlike ball valves, globe valves use a plug that moves up and down, allowing for fine adjustments. Think of it as a dimmer switch for water flow. The S-shaped path inside creates resistance, which is exactly what you want for control. Globe valves are perfect for regulating temperature or flow, like feeding hot water to a heating coil. Don't just match valve size to pipe size. Globe valves are usually size 1 or 2 sizes smaller for better control. A 2-inch pipe might need a 1-inch globe valve. The goal, precise, stable control, not just flow. It's all about finding that Goldilocks size. Let's keep going. Now, meet the smart valve, the pressure independent control valve, or PICV. PICVs automatically adjust to pressure changes, keeping flow steady, no matter what's happening elsewhere in the system. Think of it as cruise control for water flow. Set it and forget it. This keeps temperatures stable and prevents energy waste from overflow. PICVs make balancing the system much easier and boost efficiency. Sizing a PICV is simple. Just determine the maximum flow rate needed. Check the manufacturer's chart and pick the PICV that matches your required flow. No need to worry about pressure drop. The valve handles it for you. PICVs are a must for modern, energy-efficient buildings. They simplify your job and save energy. Let's move on to the next valve. 12. Time for the gentle giant, the butterfly valve. Picture a disc in the middle of a pipe. Turn the handle, and it rotates to open or close the flow. Butterfly valves are ideal for large pipes. Lightweight, cost-effective, and easy to operate. They're used for both on-off isolation and basic flow control, especially in main HVAC lines. For control, they work best between 15% and 80% open. Not as precise as globe valves, but great for handling big volumes. For shut-off, size them to match the pipe. For control, go one size smaller. Example, an 8-inch pipe might use a 6-inch butterfly valve for better control. They're the go-to for large-scale systems. Let's talk about flow and pressure next. 11. When it comes to valve sizing, two of the most important concepts you'll encounter are flow rate and pressure drop. These terms are at the heart of how well your system will perform, and understanding them is crucial for anyone working with industrial piping or fluid systems. Flow rate refers to the amount of fluid, usually water, that moves through a pipe over a certain period of time. It's typically measured in gallons per minute, or GPM. Imagine standing by a river and watching how much water passes by every minute. That's essentially what flow rate tells you in a pipe. In industrial settings, knowing the flow rate is essential for ensuring that enough water reaches every part of the system, whether it's for cooling, cleaning, or processing. Pressure drop, on the other hand, is the reduction in pressure as water flows through a valve or a section of pipe. It's measured in pounds per square inch, or PSI. This drop happens because the valve creates resistance, slowing the water down just enough to control it. If the pressure drop is too low, the valve won't have enough authority to regulate the flow. If it's too high, you might waste energy and put unnecessary strain on your system. For effective control, a valve must create a sufficient pressure drop. This gives the valve the authority it needs to adjust and fine-tune the flow, rather than just letting water rush through unchecked. Think of the valve as the steering wheel of your system. It needs enough grip to actually guide the flow where you want it to go. To visualize this, picture yourself steering a canoe. If you try to steer with a tiny spoon, you'll barely make a difference, but with a proper paddle, you can easily guide the canoe in any direction. The same principle applies to valves. You need the right amount of resistance to have real control. The goal in valve sizing is to select a valve that delivers the required flow at a calculated optimal pressure drop. This means considering both the needs of your process and the characteristics of your piping system. It's a balance. Too little pressure drop and you lose control. too much, and you risk inefficiency. A widely accepted guideline is that the valve's pressure drop should be about 50% of the total pressure drop in the circuit, or at least between 3 and 5 psi. This ensures the valve is doing its job, providing enough resistance to control the flow, but not so much that it becomes a bottleneck. By following this rule, you make sure the valve can actually modulate the flow, rather than just acting as an open gate. This is key for processes that require precise adjustments, like chemical dosing or temperature control. When the pressure drop is set correctly, you get stable, responsive control. The system reacts smoothly to changes, and you avoid sudden surges or drops in flow that could disrupt operations. Getting these numbers right means your entire process runs more efficiently, with fewer problems and less downtime. It's the foundation of a reliable, well-tuned system. Now that you understand the importance of flow rate and pressure drop, let's look at how to use these numbers to select the perfect valve for your application. Let's break down the CV formula for both water and steam. Two common scenarios you'll face. For water, the formula is CV equals sign GPM, pressure drop in PSI. This tells you how many gallons per minute a valve can pass with a 1 psi pressure drop. For example, if you need 15 GPM with a 4 psi drop, CV equals sign 15 divided 2 equals 7, 5. For steam, the formula changes CV equals sign W, 1.725x dpx P1 plus P2/2, where W is the steam flow in pounds per hour, dp is the pressure drop, and P1 and P2 are inlet and outlet pressures in PSIA. For example, if you have 500 pounds per hour steam, a 5 psi drop, and average pressure of 50 psia, CV equals sign 500, 1.725x 5x50. 500, 1.725x 15.81, 18.3. Once you have your CV, check manufacturer tables for valves with a CV just above your calculated value. Pick the closest match for precise control, whether it's water or steam. Always use the right CV formula for your fluid type, especially for control valves. This connects your system's needs to the valve's performance. With these formulas, you're ready to select the right valve for water or steam. Let's look at a special valve next. Let's explore the three-way butterfly valve, a T-intersection for water. With 3 ports, it can mix or divert flows, acting as a traffic cop in your system. For mixing, it blends hot and cool water to achieve the perfect temperature. For diverting, it sends water to different paths, like through a coil or a bypass. This keeps the system balanced and pumps happy. Sizing is just like before. Determine the required flow and pressure drop for the controlled path. Use the CV formula to pick the right valve. Always size for the path that needs control, not the bypass. This ensures precise temperature regulation where it matters. Three-way valves add flexibility to your system. Let's wrap up with the key takeaways. 12. When it comes to steam, valve sizing takes on a whole new set of rules. Unlike water, steam is compressible and its volume changes with temperature and pressure. That means you can't just use the same formulas or assumptions you would for water systems. First, always start by gathering the steam pressure and the load. How much steam flow your system actually needs. You'll often see steam flow measured in pounds per hour, not gallons per minute. Use the steam tables to find the specific volume and enthalpy for your pressure range. For sizing, the CV formula still applies, but you'll need to use the version that accounts for steam's properties. Pay close attention to the pressure drop across the valve. Too high, and you risk flashing or noise. Too low, and you might not get enough flow. Unlike water valves, steam valves are usually sized a little smaller to give better control at lower flows. Oversizing can lead to hunting, water hammer, and poor temperature regulation. Always check the manufacturer's steam CV charts, not just water charts. A practical tip for interns: double-check your inlet and outlet pressures and use the correct steam sizing equations. Don't forget to consider condensate handling and safety factors, especially in building automation systems where loads can change quickly. Steam is powerful, but with careful sizing, your valves will keep systems safe, stable, and efficient. Now let's talk about the 2/3 and 1/3 valve sizing methods, which are especially useful for steam systems with varying loads. In this approach, you install 2 control valves in parallel, one sized for about 2/3 of the maximum load and the other for 1/3. For example, if your maximum steam demand is 3,000 pounds per hour, you'd size one valve for £2,000 per hour and the other for 1,000. During low demand, only the smaller valve operates, giving you precise control and avoiding oversizing problems. As demand increases, the larger valve opens, and together they handle the full load smoothly. This method helps prevent hunting, improves control at low flows, and protects your system from water hammer. Now, let's review the key takeaways. You've mastered the basics of valve sizing. Here's what to remember. Oversizing a control valve leads to poor control. Slightly undersized is often better. Ball valves, on-off, size to the pipe. Globe valves, precise control, size smaller. Butterfly valves, large pipes, size down for control. PIX Vs, size by flow rate. The CV formula, GPM divided by the square root of pressure drop, is your best friend. Always start with the required flow and target pressure drop. Use manufacturer tables to find the right valve. Ask questions and learn from experienced engineers. Every project is a new puzzle. With these fundamentals, you're ready to design efficient, comfortable systems. Welcome to the team. Your journey as an engineer starts now. 12.